Hello and good evening to everyone. Thank you for joining us today. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 27th webinar from the IRIS webinar series. My name is Richu George Philip, and I'm a part of the Office of Global Engagement. From the Advanced Materials Technology Cluster, the research initiative presenting today is Functional Oxides, led by Professor P. Murugavel. Professor P. Murugavel is a professor at the Department of Physics, IIT Madras. He completed his PhD from IISc Bangalore. His research interest areas are dielectric, ferroelectric, and magnoelectric correlated oxides in bulk and thin film forms. Professor Murugavel has over 80 publications with more than 3,000 citations. And joining us as the moderator today is Professor Wilfred Prelier. Professor Prelier is the Director of Research at CNRS CRISMAT Amsicam at Caen, France. He's also serving as the Vice Director of the Doctoral School, EDP-SIME, University of Caen. Professor Prelier's research interest areas are thin film growth and materials physics of complex oxides, their structure, property, processing, interrelationships, functional metal oxide thin film deposition by pulsed laser deposition, oxide heterostructures and multilayers, their design of novel properties, growth mechanisms, microstructure, magnetotransport properties, and highly correlated systems. He has over 240 publications with more than 5,500 citations. Thank you for being with us today, Professor. We're very excited that you could be a part of this session. Joining us on the panel today, we have Professor Ranjit Kumar Nanda, Professor Yasir Iqbal, Professor Panchnana Khuntia, Professor Prahlad Pradhan, Professor Somnath Chandra Roy, and Professor P.N. Santosh. Thank you to all of you for being with us here today. And before we start, a note to the participants, please use the Q&A to enter your questions and upvote questions that interest you so that the moderator can prioritize them later. Over to you, Professor Murugavel.
Yeah, thank you very much for this nice introduction, and let me start. Yeah, good evening to you all, and so I'll be presenting, representing my group, in fact. So I'll be presenting the present and the current and future activities of the recently initiated functional oxide research groups. In short, it's called the FORGE. And which is actually an IOE-COE initiative research program. So let me take this opportunity to thank our director, Professor Ramamurthy, for his support. And I also thank Professor Prelier to accept for moderating this webinar. So let me introduce our team. So the members for this functional oxide research groups along with me and P.N. Santosh, so whose expertise on the oxide-based novel functional 3D perovskites as well as quasi two-dimensional layered perovskite structure, and Dr. Prahlad Pradhan, who is also working on tangent metal oxide-based super lattice structure and related field, and Dr. Somnath Chandra Roy, and so whose field of interest includes the nanostructured metal oxides for energy and environmental applications, and Dr. Ranjit Kumar Nanda, so he is a condensed matter theorist, and along with that, Dr. Panchnana Khuntia is there, so he is working on novel new quantum materials. So we also have Dr. Yasir Iqbal, so he is also another experimental condensed matter theorist involved in our group activities. So upon saying that, why oxides was so important about oxides? Oxides basically is one of the stable compound contacts. So there are a variety of oxides. It's impossible to classify everything in a simple nutshell form. So they can be classified based on their conductivity, like metal insulator semiconductors. They can also be classified based on their properties, like there are dielectric material, magnetic material, optical material, and so on. And they also can be classified based on the structure and the amorphous material, crystalline. Even if you take a crystalline oxides, and there are a variety of structures are available. I just listed some of them where our center is really interested on. So, So the perovskites, mostly we will be confined ourselves to the perovskites, apart from the layered perovskites and some of the rutile and outside structure material like zinc oxides. And so if you want to give a glimpse of the potentials of this oxides, recently the ferroelectric, even if you take a small group like ferroelectric material and ferromagnetic material, so they have applications in oxide electronics. So this simple flow chart will give their application potentially in oxide electronics. For example, if you take a ferroelectric material, recently they have been essays to show this ferroelectric canal junction, and also if you take a ferromagnetic material, so that can be used as a magnetic tunnel junction. So if you actually have a close look inside this oxide material, there are various competing interactions between the spin, orbit, charge as well as lattice. So I just given a glimpse of the different kinds of interactions exist inside this oxide and their associated energy levels. And apart from that, if we say there are some external parameters like the temperature is there, epitaxial strain is there, and then the electric field is there, and magnetic field is there, depending on their strength, and they can fall in different energy range. So by using these external parameters, and they could fall in this energy range of these competing interactions, one can change this interaction and thereby changes the physical properties of this material. So as an example, for example, if you try to make a thin film structure, and it's possible to completely form a new properties that can make a metal into a silicon insulator, insulate into metal by doing a strain engineering. So this picture shows how to do a strain engineering. Similarly, the artificial superlattice structure can be formed by stacking different layers, and that way you can create a lot of interface. It's called interface engineering, which can also lead to exotic the novel properties. So another important aspect is the dimensional confinement. If you have a superlattice structure, for example, we have an insulating superlattice structure, you can insert some conducting layers and then constrain this the order parameters. So for example, if you insert the conducting layer in between the superlattice of insulating, so the electron mobility gets constrained. That way you can create a 2D electron gas. So these are all some of the interesting stuff one can do on these oxides. So where the current stand on oxides research is that this slide will be a glimpse of where the oxide research stands. As I mentioned in the earlier slide, when you consider an oxide, there will be a competing interaction between a spin, charge, orbit, and the lattice. So depending on the kind of interaction, this can lead to an exotic properties and then novel applications. Some of them we just highlighted in the schematic diagram. The properties can be a superconducting to quantum spin liquids. And if you see, this is histograms, will give the area-wise publication list in the last 5 years. This is excluded 2020. And then these histograms will tell you about the number of publications related to the oxides. As you see here, this graphs is increasing trend as we pass the year passes, and the citations received for the papers published in oxide-related research. So these things will tell you the importance of oxide research in our day-to-day life. So what we do in the functional oxide research group. So the functional oxide research groups actually has 2 verticals. And the one is an oxide electronics, where we will be focused mostly on the application-related phenomena. So right from the photovoltaic to topological electronics. And when it comes to the second vertical, that is correlated quantum states, where the fundamental aspects of this, some of the quantum materials will be focused on. So our work plan, how are you going to do and what are you going to do, and that will be inferred from this flow chart. And as I mentioned, we have a couple of experimentalists and also a couple of theoreticians. So when it comes to the experimentalist, and our work will be on different types of material. It can be in bulk form and can be synthesized by solid-state reaction route, and also the thin films that we will be making on either pulse-based interpolation or the sputtering technique. And we also have certain plans to grow a single crystals by floating zone method. It may not be now, maybe in the later stage when we go to the second phase of this project. And when it comes to the theory theoretical members of this group, and they will be performing DFT calculations in the mean field theory and the initio molecular dynamics, and thereby they could be able to design a new oxide material with the novel applications. And along with that, it's possible to explore the emergent quantum dynamics. So once they have some kind of designs with exotic properties that can be verified by with the help of some of the experimentalists involved in our group, that's the idea. So we have a group of experimentalists and theory guys, and then we can work together and we envisage a new material design. So I'll just, in the next few slides, I'll just highlight some of the research topics which are currently pursuing in this whole project and what we are going to do in that. So it's not a complete list, it's not possible to complete everything. So there's some highlights I'll just give in this few slides. So one of the topics we are planning to focus is on the ferroelectrics, right? So ferroelectrics has a multifunctional properties. So one of the important properties, the applications of the ferroelectrics in recent days is the photovoltaic effect. For example, take about how we envisage this photovoltaic effect in a ferroelectric. Take a ferroelectric sample, it can be a bulk or it can be a thin film, right? So hold with the sample, holding in the sense you are polarizing the material. So the consequence of the polarization is there will be a bound charges. So because of this bound charges at this edges, what we see is that there will be an electric field. That field is called the depolarization or internal field. So now if you shine a light suitable to the band gap of this ferroelectric material, there will be an electron hole pair generation due to this photoexcitation process. And these electron hole, in the absence of depolarization, they will decombine quickly. But since there is a presence of internal field, the electron hole pair will get separated quickly, and then that leads to a current and its voltage. So this effect is called the anomalous photovoltaic effect. Anomalous because there is no limitations on the open circuit voltage. Unlike if you take a conventional PN junction based photovoltaic devices, the open circuit voltage cannot be more than the band gap. That restriction is not there in the case of the ferroelectric material. But there are a lot of things has to be done when it comes to the efficiency, and then in order to understand what's going on in this material, we also done a DFT calculations with the help of one of our members, Dr. Mananda. So what we have found is, apart from this polarization values, this electronic structure near this conduction band edge is also important. So it's better to have this orbital which is having orientation along the polarization direction in the conduction band edge. That is found to be more favorable for this enhanced photovoltaic effect. So there are a lot of things has to be done in this, and what we are planning to do is add more material with enhanced polarization. So do a band gap, tunable band gap by band gap engineering, and we are also planning to change this band structure by various means. So apart from that, the ferroelectrics also can be used for this for other applications. So one of the applications is that the temperature and the electric field could be used to change the polarization of the ferroelectric material. So in addition to that, recently we demonstrated that the light also can be used as an external parameter to tune the polarization. This will completely opens up a new field, a new area of applications. So we will be exploring more in this field. And another applications of the ferroelectric material is this can be used as a cooling device. It's an alternative for this compression techniques where the gases are used. So because the electric field and the temperature, by using the electric field and temperature, one can control the polarization, the entropy can be changed. So the ferroelectric material can be used as an electropolaric material. So we have just given some of our recent research where we found to have the large electropolaric parameters like adiabatic temperature change as well as isothermal entropy change. But a lot has to be done in this field because we want to use it for applications. We have to make this effect at room temperature large enough for practical applications. So, and then another aspect of our research in the forge is, you know that the magnetoresistance is also a technologically important phenomenon. So some of the rare earth magnets are known to show a large magnetoresistance, but at very high magnetic field. So if you want to have an applications of this magnetoresistance, you need to have the large magnetoresistance at low field and at low temperature. So recently, Dr. Prahlad Pradhan has seen a low field magnetoresistant, and by depositing the LSMO film on LaO2 substrate, right? And where you could see a large magneto resistance at low field, it's about Tesla, but at low temperature. So if you want to visualize or realize it in applications, so this effect has to be shifted towards room temperature, and he is planning to do the research towards this aspect. So apart from that, the interface also could affect the properties of your material, parent material. The lattice, orbital, spin characteristics of your parent material could be changed by altering the interface. That's what Dr. Palada recently has seen in some of his work. So when you try to deposit an LSMO and zinc oxide on LSMO, which is already deposited on silicon substrate, so you could see a change in magnetoresistance, which move from the positive to the negative. So, so the lot needs to be done to understand this phenomena, and is planning to extend this work in this coach group. So since we are going to use pulseless deposition, so epitaxial film is possible. So by making this epitaxial film, and we can stabilize some of this unusual metastable state. So Dr. Santosh in this group is planning to use this epitaxial stabilization technique. And for example, he is planning to use the ordered double perovskite structure, where if you try to make this in bulk form, it's not possible to have a complete B-side ordering. But if you could make a layer by layer structure by using the pulseless deposition, so it's possible to have the complete B-side ordering, so which can give a new novel quantum phenomena. So he's trying to explore such phenomena in this project. So some of this for example, if we have the antiparamagnetic insulator LaMNO3 and polyparamagnetic metal stanchium and molybdate, and if we stack it in sequence, so it's possible to have a B-side ordering, and which can be a different ground state. And if you try to make it in bulk, it's not possible to get a actual expected ground state. So he is planning to extend this studies to the other series like Rutledge copper structure, and is also planning to grow, for example, ABO3 bilayers, and if you grow along the one directions, so that could lead to honeycomb, buckled honeycomb lattices. So by doing that, he's thinking that it could be a completely different geometries and completely different symmetries. So because of that, exotic phases like quantum anomalous Hall insulators, quantum spin liquids is possible to explore. And then, okay. Then Dr. Somnath Chandra Roy, so as I mentioned earlier, so he's trying to explore the nanostructure, heterostructure, nanostructure heterojunctions for the energy applications. So in this slide, you could see some of the beautiful images where the metal oxide nanowires and nanoflux, for example, Ce2O and CO structures are seen. And here what we see is a TiO2 nanotubes and is wrapped with the graphene oxides. So these kind of structure is planning to use it for the energy harvesting, solar energy harvesting. So in addition to that, so he's also planning to capitalize the epitaxial formation of the films. So where he's planning to use the multiferrax bismuth iron oxide deposited on strontium titanate, which can form a PN junction. So the IIS is bismuth iron oxide also is a ferroelectric. There is an internal electric field, right? So the charge separation can be quickly done because of the internal electric field. That can have a profound effect on this kind of nanostructure. So when it comes to photocatalysis or hydrogen generation efficiency. So that's what he is planning to do in this project. And Dr. Ranjit Kumar Nanda, as I mentioned, this is condensed matter theorist. So he is planning to perform the TFT analysis. So along with that, model Hamiltonian. So by doing that, it's possible to create a completely unusual crystal symmetry, and then novel topological characteristics, and then interesting magnetic features, and that's what is expected to use. He's doing it, and he will be doing this project mostly on the oxide-based material. So once there is a new material is designed, so that can be immediately experimentally verified with the help of experimentalists in our group. And Dr. Panchanan Kuntia, so as I mentioned, this is working on novel quantum materials. So as you know, the frustrated, geometrically frustrated magnetic structures. So that could lead to spin liquids, right? So he is planning to explore this spin liquid phenomena in different geometrically frustrated structure like Kagome lattices, hyperkagome lattices, and then pyrocolor structure. And after making this novel quantum structure, you will be characterizing using the different techniques, novel techniques like NMR and then muon spin resonance, inelastic neutron scattering. Right? So some of the deliverables are highlighted here. Right? And so whatever I shown is only a small glimpse of which is currently going on and which we will be focusing a little bit more in detail. And apart from that, we also will be doing research on other frontier areas related to the oxides. So our collaborators for this project is Professor Wilfred Ferroelectrics from the COM, right? And he's the moderator now, is present, and along with that, Professor Shashi Satapathy from University of Missouri, where Ranjit is collaborating, and Professor Anurava Gupta from University of Alabama, and Professor Patrick Woodward, where the Santosh is collaborating, and along with that, we also have a collaborator from Nakoka University of Technologies, and Nobu Saito, and Professor Xingjiang Feng from Suzhou University, and Oman Geese from University of Houston, and Professor Karthik Shankar from University of Alberta. So what we can look for, the opportunities at present, opportunities exist in our course center. So one of the big thing is you are always welcome to have effective research collaborations, right? So, and also we also currently have one YA position. So this is a little above the postdoc, and this is applicable only for not for Indian nationals, for others is applicable. So we have opening there. And it's also, you're also welcome to join as a postdoctoral fellow. And currently the institute postdoc is not operational, but we have the national postdoctoral fellow scheme is there, and you can request one of us to be a host. So you can write a proposals and submit it, and then there's a chance of getting coming to the center from the NPDF fellowship. And the summer term project is always open, right? And shortly, we will be also conducting a workshop on correlated quantum oxides. You are welcome to join. And the short-term project opportunities for Institute, BTech, and MTech and MSc students are always exist. And then maybe the next year, the later part of next year, we will be conducting an international conference on advanced materials and interfaces. So thank you for your attention, and there is a question so we would like to answer.
Yeah, thank you, Mugavel. I don't know if you can see. There are some questions. I mean, in the text. So I'm trying to. Can you see them?
Yeah, definitely.
Can you hear me?
Yeah, I could hear you.
Yeah. Okay.
So
there's one question. The first one, which asks if ferroelectric-based storage devices with retention, it means non-volatility storage, are part of this research field.
No, actually, we are not planning to carry out this FERAM. He's asking about FERAM. And FERAM, okay, we are not planning, but we are planning to go for the ferroelectric tunnel junction. So, okay, the FERAM has some issues, but currently we are not planning to do research on that. But the ferroelectric tunnel junction is a possibility for this.
Okay. Okay, then there's a more technical question about the use of chrome plating on metal or PVC div. I mean, the person asking if chrome plating on metal on PVC differs in the process in terms of quality and durability.
Chrome plating on metal and PVC differ in process quality and durability. Somnath, can you take up this question?
Who take this question?
Somnath.
Yeah. So
Sridhar.
Yeah. So I think the question is, do chrome plating on metal and PVC differ in process, quality, and durability? So when chrome plating is done on metal, it is basically by electrochemical anodization technique we do. But on PVC, electrochemical technique does not work. So there it's simply the other vacuum-based coating techniques we used. So that is the difference. Yes, the answer is yes, they do differ in process. Quality and durability, I cannot comment on that part. That I have to see. But the process-wise, that is the answer. Yes.
Okay. Then there are some questions about, let's say, how to get engaged in this short-term project or whatever. But I guess you can. I guess these people, I mean, they will check later on with this question. I mean, I'll go more with
sorry. Let me answer that question. So the short-term project, the one possibility is institute offers summer-term projects. So due to the COVID, this year may not be possible. At least from the next year. We can apply for a summer-term project, and there is some set of procedure to be followed. And if you are shortlisted, you can come for the short-term project.
Okay. Okay. Then someone asked Savita Ramba. I mean, he asked highlight about research topics on nanocomposite using medical fields. I mean, I'm not sure if it's really part of this, but
actually, nanocomposites. Composites, currently we are not focusing on nanocomposite, and probably nanocomposite in other sense like multiferrites or magnetoelectric composite, but those are not, we don't have an idea of extending that to biological applications.
Okay. Then I have some, I mean, let's say one personal question. I mean, I'm not going to, detail all of them. What is the difference between direct and indirect electrocaloric measurements?
Yeah, but there is some issues, but indirect in the sense, direct actually measuring how much heat is generated in electrocaloric effect by using a differential scanning calorimetric technique, you can quantify that. That's a direct measurement. But generally, people they do is indirect measurement from the polarization versus electric field that will be done at different temperature, or from extract the polarization from the pyroelectric current, right? From that, using the Maxwell thermodynamic Maxwell's equation, and they will get to know the entropy change. And that has some issues because these issues becomes very prominent because of one of the, I think, the Nature paper, right? So where they quoted one of the compound, they quoted very large delta T, adiabatic temperatures, 12 Kelvin. But later, that is by the indirect way. So later, when they try to verify direct way, it turned out to be abysmally low quantity. That's why generally nowadays people don't believe you go for high impact vector with the indirect way. There's no reason. So there are a lot of issues.
I mean, okay, let me just look at the different question. Then in the meantime, I have a question about, at the end of the presentation, I mean, about photoactive multifunctional junctions. I mean, you showed that there was a tri-layer of lanthanum aluminate, then on top of strontium titanate with niobium, and then you put, I think it was bismuth iron, which was doped probably with something. I mean,
nanostructured heterojunction.
Yeah. I mean, why do you use lanthanum aluminate as substrate and you don't go directly? You don't put directly the film strontium titanate as substrate, which is already doped with niobium. I mean, it's a little bit more complicated to do this stuff, no?
Yeah. So, that is, I think, my part. You are asking that. So, yeah.
Maybe.
So, strontium titanate is also as an option. Certainly, strontium titanate directly as an option. So there are a few possibilities. I have just taken as one of the examples where we can, we can grow that. Certainly, you are right. Any lattice matched substrate we can take. So that is one of the options.
Okay, I see. And then I also know, question. I mean, I don't know which part exactly it was. When you were talking about barium 1.5, bismuth 0.5, lithium 0.5 TiO3, sorry.
Yes.
I was wondering if how is important the ordering between bismuth and lithium? I mean, is it a real ordering, or it's just mixing on the particular position?
No, it's not an ordered compound. So we didn't expect to be an ordered one. So So we didn't focus in that sense at all. It's not an ordered.
Okay. Let me check some other question. I think there was a question about direct electrocaloric measurement in electrocaloric effect. I think you answered this. Yeah, there was some question I mentioned about the superconductivity, which was also something very important in oxide and which you didn't mention. I mean, are you going to get involved in this or not?
Superconductivity currently is not in our basket.
Okay, then probably this is for undergrad students. I mean, how to choose oxides for applications?
Yeah, it depends on what kind of applications we are looked into. So, for example, as I mentioned, we'll take my own field, the photovoltaic applications, right? So it has to be a ferroelectric in nature. The band gap should be suitable to the visible range, right? And you should have the large polarization. So these are the characteristic parameter which we need to choose beforehand and go for the further studies. So depending on the applications, and there are some requirements for the oxides. So the requirements varies with the applications.
Okay, and I mean, again, I mean, when you talk about oxides, I mean, you talk a little bit at the beginning about energy applications, but I mean, there was no mention, or maybe I'm because at some point, I mean, my connection was not working properly. Are you going to work on thermoelectric materials?
Prahlad,
okay,
can answer this.
Thermoelectric material, yeah, we can plan for example, taking this insulating strontium titanate, lanthanum aluminate, how that will helpful in the room temperature thermoelectric material.
Okay, I see. Okay, let me just check if I have see some question in the meantime. Okay, well, very practical question. I mean, is it feasible? Someone whose name is Hone Agrawal. Is it feasible economically to produce nanocomposite industrially?
Yes, it's possible. Nanocomposite industry, people are doing the graphene also, graphene powder, and graphene sheets.
Then about, when we're talking about double perovskites, I mean, there's a question from Jatin Pitika. I mean, who asked, is it possible to synthesize experimentally double perovskite like calcium copper 3B4O12, as this compound are usually stabilized by high pressure? I mean, I guess the answer is yes, because I mean, okay, you can answer, but I guess using thin film, it's possible, I imagine, no?
Yeah, Santosh is a better person to answer that. So it's working on our plans.
Okay.
Yeah, so these are conventionally, as he mentioned, made at high pressure and high temperature. So whether we can make it by, I mean, thin film method, I think probably Professor Prelier is a better person to answer that. So otherwise, generally these systems are made at very high pressures, most of them. So.
Okay. Let me I have another one. I mean, how do you compare ferroelectric photovoltaic and conventional semiconductor photovoltaic devices?
Currently, the lot, as I mentioned in this talk, the lot has to be done. So if you compare the efficiency, I don't even want to mention the efficiency. Okay, but we are in the early stage. So I think it will improve, and maybe in another 5 to 5 years, so we can catch up. And, plus, compared to other advantage, as I mentioned, is the open circuit voltage. There's no limitations. But currently, the issue is the short circuit current is very, very low. So that can be improved by various means. But people who are focusing the research on these topics, very, very few numbers. So if more people join, it's possible to take up this up to that level. Currently, it's little low.
Okay. But let's say, talking about this photovoltaic, I mean, what kind of, let's say, value are you expecting to reach? I mean, let's say to turn into real application.
So anything like 10% efficiency will be better.
Okay. Let's say above 10%, you mean?
Long way to go. But there's no limitation. Okay. But we don't know. Anything can happen. So a lot of research has to be done on this. So it's just starting.
I see. Okay, what else? Let me just check if there is. What what is possible? Okay. What do we have?
So Somnath, you can help me.
Yeah, I mean, let me check. Chrome. Yeah, I've also no. Let's say one question. When you were showing, you know, the stacking between LSMO, I think this was grown on silicon, and then you put on top of zinc oxide.
Yeah.
Yeah, I was a bit surprised about the, you know, let's say talking about strain. I mean, when you grow LSMO on silicon, I mean, mismatch will be very huge. And then, if I remember correctly, I mean, zinc oxide has an hexagonal structure, which might be difficult to grow on long LSMO, which is more perovskite structure.
Yes, if you grow LSMO on silicon, then silicon 110 will pick up.
Okay.
So that that is there on the surface for 001 orientation. So that has a very reasonable mismatch, less than 1%.
Okay.
Close to 1%. And then when you have 110 on the surface of this LSMO, the 110 surface, ZNO, then it has a matching on the 001 or 100 of ZNO match with the 110 of LSMO. So then it's better matching. So instead of like, if you grow ZNO directly on silicon, you don't see good variation in the thickness at 700 degrees centigrade. But if you grow ZNO on top of LSMO, it gives a good thickness variation as well as band gap variation.
Okay.
So that we observe. Okay.
Okay. Again, I'm not sure. I don't know who can answer this. I mean, when you were talking about the ordering of double perovskites, I mean, can you remind me, I mean, along which direction is this ordering? I mean, is it along the 001 direction or not? I don't think, I think no.
Yeah, I mean, so the idea in this case is try ordering along the, you know, 111 direction will be the ideal thing.
But
so that's going to be difficult. I think that's why I think not too much work is there. So I think ideally it should be along the 111 direction. So.
And is it a one ordering?
Yes.
Okay,
you
so
mean
it's
BB prime ordering, right? So
yeah. Okay, that's what I say. Okay, good. Let's say, I mean, okay, let me check. I don't know if you see more questions, but
why mixing up graphene or graphene oxide enhance the properties of, example, metal oxide plus graphene? Somnath?
Yeah. So the graphene oxide is, first thing is that not exactly graphene, but still we have managed to tune the properties in a way to get better conductivity, so that when we wrap around the metal oxide nanostructure and when you shine light on that metal oxide, electron hole pairs are generated. And then this graphene oxide, actually reduced graphene oxide layer, was able to collect some of the electrons out of the metal oxide structure. So in that way, it was actually helpful to actually separate the photogenerated charges. And that leads to increase in the photocatalytic efficiency. So we are doing further work on that now.
Okay. Let's say what is okay. When you grow all your films, I mean, you use the PLD. I mean, don't you think that at some point, I mean, this will limits the, let's say, applications? I mean, because, you know, due to size of the substrate and so on. I mean, what do you think about this? I mean, it's more broad question.
True, but whatever PLD is mainly for research. Once we establish that this system is showing, then there are other techniques to deposit the same quality.
Okay. Yeah, I mean, I don't know if I think are there some more questions which I didn't mention? No. Let me check. Mixing of question, we have the answer, and so on. How to choose? Nanocomposite, electro. About the ordering, superconductivity, we answered. Yeah, I mean, I have another one. When you were talking about the, let's say, magnetoresistance, let's say positive magnetoresistance, what are the reasons behind this positive magnetoresistance? I mean, in conventional CMR, manganese-based material.
Okay, so we know that the scattering process is always associated with the conduction electron. So that provides the resistance of the CMR material. So when you observe positive magnetoresistance, that this indicates that the scattering processes increases when you apply some magnetic field. So when you talk about positive magnetoresistance, you need to characterize it other properties and find out the associated process. So here we try to understand from the out of plane positive magnetoresistance, and it shows that the magnetoresistance is associated with spin orbit coupling, and this spin orbit coupling induced weak antilocalization. But if you see the same thin film, it shows positive magnetoresistance at very low field in the in-plane direction. But when you go for out of plane direction, it's shows for a wide range of magnetic field. So magnetic field is relatively high. So that indicates that there is some presence of local antiferromagnetic coupling, which dominates over the Zeeman energy. So overall, if you see the spin orbit coupling as well as local antiferromagnetic coupling, they are the source for the positive magnetoresistance in this material, in this thin film.
Okay. And I mean, then I have just a final question, because I didn't got the point. I mean, what are the typical applications for electrocaloric effect?
The electrocaloric effect is applies is cooling devices. Is also a refrigerant material.
Okay.
So.
Okay,
yes, it's
kind of similar,
mobile,
like
even for the mobile heating effect with the cooling device, it's mostly small electronic devices we can use.
Okay. Okay, fine. Okay, I guess I don't know if we have more questions, but I guess we are close, no?
There is one question. I say how the advancement of material will help to improve the efficiency of solar something like that.
Oh yeah, how advanced in materials help in efficiency of photovoltaic cells in present use?
Yeah, I think people are going for the hybrid solar cells, where they are trying to combine the silicon-based solar cells and then perovskite-based solar cells. So that way they can increase the efficiency above around 22 also is possible. Our IIT Madras also has solar hub some research is going on.
Yeah, but in that case, it's not really oxides. I mean, it's more organic perovskites, no?
Okay. It's not directly related to our work, but that's a general question.
Yeah, of course. Okay. I mean, who has more questions? No, nobody. Did we answer? I mean, did Murugavel and his group, answers most of them? No? Yeah, I think so, no?
We are answering.
Okay. Okay, so, I mean, I don't know, are we done or? Yeah.
Professor Murugavel, we can wind up the session if you think we've answered most of the questions.
We answered most of the questions.
Yeah, all right.
I think so, yeah.
I'm also typing some of the answers directly.
Okay, but I cannot see what you type actually.
I mean, yeah, and whatever, so that to respond to as many as possible.
Yeah. But I guess, I mean, if people are more questioned, I mean, they can answer, they can email directly.
Yeah, directly.
Sure.
Yeah,
everyone will be happy to answer some.
Thank you so much, Professor Wilfred Prelier, for being with us here.
Yeah, thank you. I mean, it was a pleasure for me.
Have you here and,
yeah.
Spend
Pleasure.
This
I
time.
mean, good luck for all of these projects. I mean, it sounds very interesting, and I mean, I'm sure you will get many very interesting things from all of this research.
Yeah.
And also convey all my regards to all of my colleagues and friends in India.
Sure.
Thank you.
Hopefully you can visit us soon too, sir. Thank you.
I hope so. I mean, I hope yes. Take care and stay safe. Okay.
Thank you.
You too.
Anyway.
Thank you, Wilfred.
Thank you, Professor Prahlad.
Thank you.
Thank you.
Have a good evening.
Thanks to everybody.
Okay. Good evening. Thank you.
To all of the participants. We do have another webinar coming up. Please do join that as well. And please write to us if you have any questions, and Professor Muruga will be happy to answer them. So that's all. Thanks a lot, everyone. Thank you.
Thanks.
Thank you.
Thank you, Professor
Bye-bye.
Prelier.
Thank you.
Thank you.